Um, and or better yet, talk to him. So thank you so much for coming here and visiting us today. Frieder is the leading geochemist, particularly in oceanic settings, and he's at the Oceanographic Institute. And he's going to tell us about hydrothermal alteration of mantle rocks producing hydrogen mechanisms.
Thank you so much. Really excited to be here. It's been a while since my last visit to MIT. And I want to say some of what I presented last time was already published, and I'm not sure if anyone was here in the audience that time. It was probably like 2011 or so, 2012. Anyhow, so I'm going to talk about geologic hydrogen in oceanic settings, and I will talk primarily about a process referred to as serpentinization. Some of you may have heard about that. For those who have not, it's basically the reaction of mantle rocks with water to form a rock that is primarily composed of serpentine group minerals. And I chose this slide, this photomicrograph as my cover slide because it shows the process in its entirety. So going to completion. And what I'm talking about are these unsuspicious looking black dots here that we refer to as fluid inclusions. And these fluid inclusions are filled with hydrogen and methane and serpentine. So water that was percolating through the rock at some point got trapped at elevated temperatures and pressures. And then as the rock cooled, the serpentinization process began. And because these are closed systems, all the reaction products are still present. And because olivine, which is the host mineral that you can see in yellow here, is a far greater abundance than the water that was trapped in these micrometric inclusions. I think I covered the scale, unfortunately. So this is maybe 5 microns across. And because the olivine is the reactant that is in much greater abundance, and water was the limiting reactant, this reaction went to completion until all the water was consumed and as much hydrogen was produced as possible. Okay, so why would we care about geological hydrogen? And from a marine geology perspective. So in general, the formation of hydrogen as a reduced phase results in a net oxidation of the oceanic lithosphere. It facilitates abiotic organic synthesis reactions that, so for example, the formation of methane, but also other organic compounds that may or may not have played a role in the emergence of life on Earth and possibly other planetary bodies. The hydrogen supports microbial life with chemical energy independent of sunlight. So we're talking about chemolithoautotrophic environments or settings. And as I just mentioned, the process is also known to occur on other planetary bodies. Well, at least we can infer that it's happening. And as Laurent already mentioned, there's also a recent increasing interest from a hydrogen economy point of view. So the major sources of geologic hydrogen are summarized in this cartoon, and we published that in 2020. This is like a very accessible paper meant for the general public. Or like scientists with only a general knowledge about geology. So we have 4 major processes. One, we have radiolysis, mechanoradical hydrogen formation, volcanic degassing, and hydrothermal alteration. So in the first case, we have the decay of uranium, thorium, or potassium, alpha, beta, or gamma decay in the presence of water, and that causes basically the formation of hydrogen, but also other products, including oxygen, peroxide, and water itself, as things recombine. Mechano-radical hydrogen formation is similar. Now, the driving force is not radioactive decay. Here it is rock comminution. It's the frictional process that rips bonds apart and in the presence of water and allows the formation of these silica compounds and hydrogen. Then we have volcanic degassing. The main reaction here is this one. It's hydrogen sulfide plus water makes SO2 and hydrogen. Now, when you go on land, that is actually not an insignificant source of hydrogen, but this reaction is highly pressure dependent. So the equilibrium shifts towards sulfate and hydrogen with decreasing pressure. At seafloor pressures, this is not a relevant reaction, and much of the sulfur is actually present as H2S. So what I'm going to focus on today is this hydrothermal alteration, specifically serpentinization, where we have the oxidation of ferrous iron to ferric iron by water, and that is generating hydrogen. There's another reaction that is taking place in the salt-hosted hydrothermal systems, which I'm not going to dwell on today. So again, serpentinization is a process where you have the reaction the reaction of mantle rocks, mainly composed of the minerals olivine and pyroxene, with water to form a rock that we refer to as serpentinite. So this process turns a dry, dense, mechanically strong, and weakly magnetic rock into a rock that contains abundant water, that's less dense, that's mechanically weak, and can be strong. So that's serpentinization in a nutshell. Where does serpentinization occur? In oceanic settings, we have slow spreading mid-ocean ridges, rifted continental margins, as well as subduction zones where serpentinization can occur, both through bending-related faulting, where seawater trickles down through the ocean across into the lithosphere. That process has been proposed, was it 2004, and there are a lot of folks who strongly believe in this process. I'm a little skeptical that it's actually happening, but for the sake of completeness, I'm including that here, as well as we have serpentinite mud volcanism or serpentinization in subduction zone cores. And subduction zones are these areas where the oceanic lithosphere is descending underneath the continental or another oceanic plate. And then we have ophiolites, which are pieces of oceanic crust and mantle that were shoved on land by tectonic forces. There was a cool study by Andrew Meredith and colleagues in 2019 who estimated the cumulative serpentinite thickness in oceanic settings. And this is a really rough approximation of what could potentially be there. The underlying assumption here is that the serpentinite abundance scales with the spreading rate. So there's more serpentinite present in slow spreading and ultra slow spreading environments, and less so in fast spreading ones. That is a very crude assumption, but like he was the first one who had the guts to put it out there. So I think it's a good starting point for discussion. And there's direct evidence for hydrogen formation in seafloor hydrothermal systems. Here we have three different types. We have a basalt-hosted hydrothermal system. We have a mantle rock, gravitite-hosted hydrothermal system that is undergoing serpentinization, and we have a hybrid system. This is a tag hydrothermal field. This is Logachev, and this is the Lost City hydrothermal field. So for a scale, anyone who has driven to Cape Cod and went over the bridges, the height from here to here, this is a mosaic, but is about the same as the bridges are tall, so like about 55 meters. So these ones are smaller. And when you look at the fluid composition of these vent fluids that are emanating from these structures, they show significant differences in the hydrogen content. So the hybrid and serpentinite hosted systems have abundant hydrogen, whereas the basalt hosted hydrothermal system has low concentrations of hydrogen in general. There are other chemical differences that we can talk about later. So I briefly mentioned the serpentinization systems in the subduction zone forearcs. So we have the descending oceanic crust goes across an overlying sediment, undergoes the volatilization or compaction first, and then dehydration, and the water rises through the through faults, migrates through the overriding forearc mantle, and leads to serpentinization. And because serpentinite is less dense, as I mentioned before, it rises buoyantly through these faults, forming large serpentinite mud volcanoes that you can see here in this map. All of these are not here. These ones are serpentinite mud volcanoes. It can be up to 2 kilometers high and about 50 kilometers in diameter. Yeah, this is just like a side scan sonar image and a seafloor photograph where we have spindles of brucite and calcite forming as the fluid that is highly alkaline mixes with seawater. Another important setting for serpentinization reactions to occur are passive margins, so continental margins, ocean continent transition zones. This is just like a general map of all continental margins. Where serpentinization is particularly prevalent are magma poor passive margins, such as the Iberian margin and the Newfoundland margin. And here is a cross-section of the Atlantic Ocean when it was just opening up, so in its embryonic stage. And the idea is that the continental mantle during breakup was pulled out by tectonic forces. And so the mantle then was exposed to seawater that was filling this basin and led to widespread serpentinization reactions. And at the Iberian margin, there were several expeditions by the Ocean Drilling Program, now International Ocean Discovery Program, and they recovered rocks that used to be mantle rocks, mantle peridotite, and that underwent strong extensive alterations, so serpentinization, but then subsequent weathering. So we go from the top deeper, and then this is the next one, deeper, 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 to this is the deepest portion. And what you can see right off the bat is that there are these differences in the color, and that represents differences in the oxidation state. So here, the rocks are much more oxidized than in this part. And when I sampled these rocks for a project to learn about reaction pathways to serpentinization, I was intrigued by a mineral that looked pink. I thought someone dyed it somehow, and I was just curious like what it was. And it was right next to this vein. And this vein is composed of calcite and brucite that forms during mixing of serpentinization fluids with seawater. And inside these veins, we found these lipids And some of them are actually intact polar lipids, similar to those that are present in the Lost City hydrothermal system that I talked about earlier. With the difference that these are about 100 million years old. So this is an ancient system that was active during the breakup of Pangea. There are mantle rocks in continental settings, and Olli Jahwitz, who's in the audience, published a paper recently on Monday, was it, I think? Nature Geoscience paper.
Yesterday.
Yes, yesterday. Yep, on weathering of ultramafic, mafic and ultramafic rocks and ophiolites. And this is a compilation of all the ophiolites that are present in, that we know of in continental settings. And some of these are very old. And we know that this process of serpentinization has occurred basically since as long as the Earth is old. It's a very, very old process, and even probably before then on meteorite parent bodies. What these look like, these systems, so they're active serpentinization systems like here in Turkey, where you have hydrogen and methane seeping from the ground, and these are called eternal flames. They're known to have burned since, I think, 2,000 years or something like that. Still ongoing. And then there are fossil systems like here is the Josephine ferritite. This is placed in Cyprus, and this is not too far away from here in Rochester, Vermont. This is a Mount Belvedere, which is a Superfund site, also in Vermont, in the Appalachians. We look at the physical property changes. They're quite dramatic, and they can be summarized on this awesome diagram. I like that quite a bit because it's very simple and relatively easy to understand. So the extent of serpentinization goes from 0 to 1. So this is completely serpentinized. And so we start out up here where we have no water content. We're basically a dry rock. And as we add water and form hydrous minerals, the water content increases and the seismic velocity decreases, as does the density. At the same time, we have a decrease in the mechanical strength of the rock, and also an increase in the magnetization in some cases. Now I'll get back to that later. So this is an example of a magnetic map of the seafloor in the rainbow hydrothermal field on the Mid-Atlantic Ridge, where you see these red areas here that have a high, shows high magnetic signal, which is due to the formation of magnetite through the serpentinization process. And we looked at one of a related process here, which is the volume change during serpentinization. And there was a lot of discussion about whether serpentinization is actually a volume increasing process or not. And the reason for that is that some people say that much of the magnesium and the silica that is in the ferritite gets removed during serpentinization. And so when you look at the fluid chemistry of hydrothermal systems, that's actually not the case. So the magnesium and the silica, which are the predominant compounds or elements, are largely conserved. And so what we did is we were trying to quantify this, and not just like on theoretical grounds. So we performed hydrothermal experiments where we took like little chunks of rocks. This is a scale bar. So these are a few millimeters across, and place them into a gold capsule together with an aqueous solution, which is similar to seawater, and that sits in a pressure housing, and it sits then in a tube furnace. And we did these experiments at 300 degrees C and 35 megapascal for up to a year and a half, and we did CAT scan before the experiment and after the experiment. These are radiographs. So, and we use spinel, which is a mineral that is quasi-inert during the reaction, as markers in a 3D coordinate system and measured the distances of the spinel grains before and after the experiment to see how much they moved. And yeah, this is an example here. So we have a reference spinel, and then we have all these other spinels, and it's a scale. And then you can see that it's not a homogeneous expansion in all directions. It is quite distinct and hard to predict at this point how and where and why these movements are different. And these two diagrams show the days of reaction or the experiment and or the duration. And then here we have the volume change in the reacted rock and the extent of reaction. So as you can see here, the extent of reaction is in terms of weight percent of the protein. So in the case with the highest extent of reaction, only 6% of the rock has reacted over the 18 months period. And the overall distance change was fairly minor, right? So you could say like, oh yeah, this is a trivial volume increase. But when you normalize the distance over the extent of the reaction, then you get the true volume change for the reacted portion of the rock, which is close to 45 volume percent. And that is as much as you would expect if the system would conserve the magnesium and silica during the reaction. Speaking of reactions, so there are serpentinization reactions that can be depicted in the simple ternary chemograph. I promise I won't show too many chemical reactions today, but when you start out with a fresh mantle rock is composed of olivine and pyroxene, here represented by the magnesium end members. Now, if you take olivine and you add water, right? So you add water, you walk towards the H2O apex, and you cross the line of serpentine and brucite, and that's exactly what you make. So you make serpentine and brucite, and it is this first reaction. So this serpentine, that's brucite. You can do the same thing with pyroxene. You add water to pyroxene, and you make serpentine and talc. If you have olivine and pyroxene in the right proportions, 50-50 in this case, then you will end up with serpentine only. So you can see that there's a compositional effect on the formation of secondary minerals. Now, if you were able to add silica or remove magnesium, you could make talc only at the expense of pyroxene. But you all, or some of you at least, are interested in hydrogen formation, so we need to consider the role of iron. And here are two simplified reactions that generate hydrogen. So you have iron, ferrous iron that sits in olivine and pyroxene, reacts with water to form magnetite. And you can see that in this backscattered electron image. This is the olivine that we reacted in a hydrothermal experiment. You can see dissolution pits here, and as well as up here. And then you can see the formation of euhedral, so ideally formed magnetite. And then you can also form hydrogen through the formation of ferric iron in serpentine, and the serpentine is the fuzzy stuff here. So serpentine is not of the pure magnesium composition; it contains ferrous and ferric iron. So the more ferric iron you have in this serpentine mineral, the more hydrogen you can make. But then there are competing reactions, such as the hydration of ferrous iron here in olivine to ferrous iron in brucite, and brucite is this big mineral here. So the more ferrous iron is included in this brucite mineral, the less hydrogen you will make. You can see that this is not producing hydrogen. And at the same time, we have this ferrous iron component in serpentine that also does not generate any hydrogen. Now, this diagram here is a little busy, and it actually shows how complex serpentinization reactions can be. So it shows the magnetic susceptibility versus density. So we start out with a unaltered piece of mantle rock, and then we add water, right? And so we decrease the density, and if we make magnetite, we increase the magnetic susceptibility. And so if this was a single reaction, the reaction would just plot in this trajectory. But there are examples in the literature where there's no magnetite formation. So if magnetite is an important reaction product for hydrogen formation, or a key mineral for hydrogen formation, what does it mean if they're completely serpentinized periddotites, but they don't contain any magnetite? And it was like a conundrum for quite some time. So our approach was to use theoretical models, thermodynamic tools that allow us to calculate the fluid speciation and solubility of minerals, to develop geochemical reaction path models. The tools we use are SUPGRID and EK36. What we need is as input, we need the composition of the rock or the mineral. We need to know the dissolved species and pH, as well as pressure and temperature of the fluid. We need appropriate activity models and thermodynamic data for standard state conditions, as well as heat capacity data for elevated temperatures and pressures, as well as appropriate equations of state and solution models to calculate the equilibrium model constants at these elevated temperatures and pressures. And this does not include any transport, any kinetics. This is the very first step to go from looking at simple systems that don't account for ferrous and ferric iron solid solutions in minerals to some that actually do. And so it's really simple to understand the process. So we take seawater, we calculate the equilibrium speciation of seawater. So what that means is like what is the components that are in seawater, dissolved in seawater, how are they chemically arranged. Then we add a solid reactant, in this case olivine or peridotite, and then we change the temperature. We heat the system up and we look how the composition of the fluid and the rock changes. And that's shown in these two diagrams. In the simplest case, we have a model for olivine, the most abundant mineral in peridotite, as well as one for pyroxene. And so temperature versus predicted mole percent of minerals. So you have olivine stable at temperatures higher than about 350 degrees C or something like that. And then as you decrease the temperature, the olivine becomes unstable and reacts to form brucite, serpentine, and magnetite. But our models only predict magnetite to form to about 200 degrees C. Below that, much of the iron is actually being sequestered into brucite. Brucite likes to host ferrous iron, so that would suggest that there's limited hydrogen production, but that's actually not the case because, as I mentioned earlier, serpentine also can host ferric iron and therefore contribute to the formation of hydrogen. So brucite becomes richer in iron or less magnesium as temperature decreases, which then limits the formation of magnetite. That's the prediction. For pyroxene, we don't form any magnetite at all. And the reason here is that the serpentine that forms as a reaction product is quite iron rich. So there's no room or no thermodynamic drive to make magnetite during the reaction with pyroxene. When we look at the predicted hydrogen production, we can see that the hydrogen production changes with temperature. This is olivine forsterite 90, so this is the typical composition of olivine in the Earth's mantle. We can also use combinations of olivine and pyroxene in And this is not olivine 4-70, it's just like 70 volume percent olivine, 30 volume percent pyroxene, and different water flow operations. So I could choose any combination of this, is really not important. But the key here is that we generate a lot of hydrogen and that the absolute concentrations that we're predicting are quite variable. And that for comparison, our measured fluid compositions from these different hydrothermal fields on the Mid-Atlantic Ridge. And we could match those really well and say, that, oh yeah, we understand what's happening, but there are no unique solutions. So I can basically make it fit if I want to. And so there are still things that we don't understand why, how much hydrogen is produced. But the key here, another issue or thing is I want to mention is that we do produce quite a bit of hydrogen, can produce quite a bit of hydrogen at low temperatures from a thermodynamic perspective, because there's quite a bit of ferric iron in serpentinization, even though there's some magnetite formed. There are obviously kinetic issues that we need to take into account, and I'll talk about that in a little bit. So when we look at, we'll go from the theoretical predictions to the rocks that we collect from the sea floor. Here we have a half spreading rate map of the seafloor. So we have samples from the slow spreading Mid-Atlantic Ridge. We have samples from the Iberian margin, the Tyrrhenian Sea in the Mediterranean, as deep as well as from the Mariana Fork. And again, the slower spreading ones are supposed to be supposed to produce more serpentinized, thus more hydrogen than the fast spreading ones. And when we looked at these rocks, and these are two backscattered electron images that I took with a scanning electron microscope, there was a difference between, directly apparent difference between these two sites. So this is Mid-Atlantic Ridge, and this is the Iberian margin. Here the gray material here is serpentine, the white is magnetite. There's also a little bit of bluesite in there. When we submitted this for publication, one of the reviewers said, well, why would you include this BSE image? It doesn't really show anything. And we're like, yeah, that's the point. There's no magnetite forming here. The idea would be that magnetite formation is controlled by or influenced by the alteration temperature. As I mentioned before, 200 degrees C and higher, there's a lot of drive for magnetite formation. Lower temperatures, not so much. So we want to know what is the temperature of alteration. But I also want to point out that these are backscattered electron images of really minuscule, tiny grains of the warroite, which is a nickel iron alloy that is only stable at extremely reducing conditions. So suggesting that even though there's no magnetite, there is still a lot of hydrogen that was produced. Now, these are two busy plots, and I'm not going to spend too much time on this, but like we did electron microprobe analysis to determine the composition of the serpentine and bluesite formed during serpentinization at different settings. And these are these different ODP rates that I mentioned earlier. So we have iron-rich bluesite plotting here, and this is iron-poor serpentine, and these rocks that have iron-rich bluesite also have relatively low low magnetic susceptibility. So these samples here are from the Iberian margin, the ones that don't have magnetite. So the idea, again, or the prediction was that with decreasing temperature, that bluesite takes on more iron, leaving less room for magnetite. And that is reflected in these measurements. So these are indeed iron magnetite pool. So we took oxygen isotope thermometry data from the literature, and we see a bimodal distribution. So the samples from mid-ocean ridge settings tend to be hotter than the ones from the Iberian margin. So this confirms that there's an effect of temperature on the reaction pathways during serpentinization. Specifically here, the magnetite production and the iron content of brucite. We can use these activity diagrams. It would take me a while to explain exactly what's going on here, but like these are theoretical models that allow us to assess how much hydrogen and H2S would be in equilibrium with a specific mineral assemblage. So I pointed out this mineral warite before, and it occurs together with another mineral, which is a nickel iron sulfide. It's called pentlandite. And so we know that pentlandite and the warite can be stable at conditions that are really, really reducing. And we know the temperature of the alteration. So we had about 150 degrees C for these Iberian margin samples, 150 to 200 degrees C. So we can get an idea of how reducing the system was. And so the predicted concentrations here would be about 30 millimole per kilogram. We can also use mass balance constraints to figure out how much hydrogen is produced through the abundance of ferric iron in the rock, and that gives us roughly the same amount. Now, I want to talk a little bit about the experimental constraints on hydrogen formation. And so what we do here is we take a gold bag like this, and it has a titanium fitting, and the rock sits in here, can be a powder, can be a solid rock. That's together with an aqueous solution of our choice. We have this fitting that allows us to take samples during the experiments. This sits in a pressure housing, and it sits in a tube furnace. You can control temperature and pressure and measure the fluid composition without the presence of a headspace. So there's no free gas space in there. And people have done that for a while. And this is a diagram that Bill Seifried from the University of Minnesota made in 2007, I believe. Yep. And so he calculated, well, he measured the hydrogen formation during serpentinization of a mantle rock at 200 degrees C. And what he found was that there's a lot of hydrogen being formed, but it's about 4 times less than the prediction. And the reason here was, and that's a mistake a lot of people make when they first are exposed to serpentinization reactions, they do not consider solid solutions. Solid solutions are really important in understanding the hydrogen formation, accurately predict the hydrogen formation. So here we have the reaction olivine, so magnesium and iron react to serpentine, brucite, and magnetite. So you notice that serpentine and brucite in this case are do not contain any iron. So all the iron that is originally contained in here is allocated to the magnetite. And if you do that, if you make that mistake, then you will predict about 4 times more hydrogen formation than actually occurs. DOE would love that until they see the harsh reality of what the hydrogen production actually is. The other thing is that I lost my train of thought. Sorry. Well, anyhow, so like let's move on here. So when you write the actual reaction, and we'll see if he came up with the actual reaction, that looks a little more complicated. It looks like this, but he did not have the thermodynamic data in order to calculate what's happening. We actually included all the solid solutions in serpentine and brucite in some of our papers, and we're able to more accurately predict and then confirm the hydrogen formation during serpentinization. And so this is a study that Tom McCall and I did in 2016. We looked at the effect of temperature on the hydrogen formation rates. And you see there aren't actually all that many experimental studies because it's not necessarily trivial to measure the hydrogen formation during serpentinization in a laboratory environment. We see an effect of temperature, right? So you have the highest hydrogen formation rates at about 300 degrees C, and they tend to drop off towards lower temperatures. And it's a fairly consistent picture. The hydrogen production rate is also dependent on the grain size of the reactant. So the smaller the grain size, the larger the surface area, the faster things react. There's this outlier here, and I'm not exactly sure what happened here, but that's from a different study. Now, when you look at the serpentinization rates, there are different ways of measuring serpentinization extent as a function of time, so you take density, magnetic susceptibility, or other parameters to determine the extent of reaction over time as a function of temperature. And what you end up with is basically a bell-shaped curve where you have the highest reaction rates somewhere between 200 and 300 degrees C. And as you go towards higher temperatures, 400 degrees C, you actually reach approach equilibrium, which then puts a boundary to it. So once the system reaches equilibrium, there's no hydrogen production anymore. And at low temperatures, it's basically a kinetic effect. These ones up here are doped with aluminum. There was Muriel Andriani who came up with this. Yeah, there's a more recent study. There was Hector Lamadrid and I and a couple others who compiled all the data. And you can see that there's a significant spread. And like there's orders of magnitude differences. This is a temperature and then log J. This is Don Rimstead, one of the really big names and reaction kinetics and earth sciences. He passed away not too long ago. But he came up with this log J, and it's basically moles per square meters per second approach or number for these serpentinization reactions. It's a little tricky because you have to make assumptions how to recalculate the results from previous experiments. What you can see again is there's a huge spread, and some of that is due to grain size, but there are other factors in here. And I want to briefly talk about serpentinization experiments that use one powdered reactants, which is easy and nice because you have a reaction that is relatively rapid due to small grain size and large surface area. The experiments can go to completion on lab or industrial timescales. The cons are the textural features that are lost during grinding. It's not a real rock anymore, and hydrodynamic effects and fracturing cannot be studied. And obviously, if you think about underground extraction of hydrogen from a real rock, unless you frack the Jesus out of it, it will be a solid rock. So we decided to use a solid rock as a reactant, and we believe that this is probably closer when it comes to reaction rates to the actual geological system. The cons are excruciatingly slow reaction rates, and we have a lot of power outages on the Cape. So if you run an experiment for a year and a half, and there's the nor'easter coming in, yeah, it's unpleasant. So we used mantle peridotite, a fresh unaltered mantle rock from the Methane in Germany. These are thin section photomicrographs and Klein and cross polarized light. Yeah, at 300 degrees C, because just more favorable reaction conditions, we reacted that for about a year and a half. And you can see here the hydrogen concentrations of our experiment. They increase rapidly at first, but then taper off. And for comparison are shown experiments that used powdered reactants. Here, with this, you have rapidly increasing hydrogen concentrations. They're also tapering off at some point, but the difference here is really the extent of reaction overall was pretty small. And I'll get to that in a moment. We checked the fluid chemistry as a function of time, confirming that magnesium and silica are conserved. The main reaction products here were serpentine. Chrysotile is one of the serpentine minerals. We did not make any brucite or talc, which came a little bit as a surprise. These are backscattered electron images of the rock that we extracted after the experiments. And we analyzed the mineralogy. So we have lizardite, magnetite, so there's magnetite form. There's also calcite. And you have reacted rock for minerals here. There's an orthopyroxene. And sulfur poor sulfides, hazelwoodite, suggesting reducing conditions. These are backscattered electron images of slices that we made from that rock that we cooked. And you can see these darker areas, that is where serpentine formed, and you can see these dissolution pits where the olivine dissolved and serpentine formed. And this is helping drive the reaction because the volume expansion during serpentinization basically pushes this apart. What we could also see is that orthopyroxene was much more reactive than the olivine by comparison. You could also see that the olivine actually made magnetite here. This is the exterior of the rock. So magnetite and serpentine, whereas like the orthopyroxene only made serpentine, lizardite in this case. And it's consistent with these simple, really simple models that I showed you earlier, that the iron content of serpentine is higher, that forms at the expense of orthopyroxene, not leaving any room for magnetite formation. And we use different approaches to determine the extent of reaction. What it boils down to is about 4% reacted over the course of a year and a half. That's not fast. And we can play around with the reactions, but we know that there was 4 times more olivine than orthopyroxene in this rock. We only made serpentine, and if you take the mass balance into account, we have to come to the conclusion that orthopyroxene dissolved about 2 times faster than the olivine. So the relative reaction rates of the olivine and the orthopyroxene also have an effect on the hydrogen production and the reaction products. Now we have some more elaborate models that take reaction or dissolution kinetics into account. Here, the assumption that we have orthopyroxene reacting about 2 to 4 times faster than olivine. And we can compare so this is the model prediction, and this is this is the end of the experiment, which is pretty much consistent with the prediction, the relative abundances of these minerals. We can compare our measured hydrogen concentrations with the predicted ones. We can compare the pH, and it's not perfect, but it's getting much closer to reality than previous studies managed to accomplish. And here we have just how the different iron species are distributed. So we have ferric iron and serpentine, ferrous iron and serpentine, ferric iron and magnetite, and ferrous iron and brucite. And the distribution of ferrous and ferric iron here dictates in the end how much hydrogen is being produced. So to sum this part up is we have hydrogen concentrations, formation rates change as a function of temperature, rock composition, but also on the relative reaction rates of primary minerals, but also fluid access to primary mineral surfaces. Because as you could see, the reaction was significantly slower when compared to a powder, right? In a powder, you have a lot of surface area, whereas in a rock, it's much more challenging or difficult for the water to access these reactive surface areas. So fracturing here is key, and we're talking about thermal contraction or thermal fracturing, tectonic fracturing, and then also reaction driven fracturing, which is this example here. So I realize we're about approaching the hour. I could talk a little bit about methane if anyone is interested, but if not, that's cool too. Really up to you, because there's the general assumption that CO2 likes to react with hydrogen to form methane, right? So if that reaction is happening, that decreases your hydrogen yield, right? So it's part of the story, but I realized I was talking a little long for the first part.
I mean, how many slides is it?
And we can quickly go through it there.
Just
Okay.
points of the rest.
Yeah, I might skip through a couple. So the general assumption is that we have seawater percolating through the oceanic crust. Seawater has about 2 millimole of CO2 that is being reduced by hydrogen formed during serpentinization to form methane. That is then venting from these chimneys. And there have been stable isotope studies that don't really give a clear picture of like the sources of the methane, because the methane can be abiotic, can be thermogenic through heating of organic matter, but it can also be microbial, and there's significant overlap here. The problem with this assumption here is that much of the methane is radiocarbon dead. So it's like close to 50,000 years or older. And if this reaction was rapid, right, we would see a significant fraction of the of recent or young carbon in the methane, but that's not the case. Even though the timescales on which fluids percolate through the seafloor is on the order of a few years to maybe a few thousand years. So this is consistent with the measurements in hydrothermal fluids, where we see that none of the CO2 that is present in seawater is actually consumed to form methane. So there's more carbon in total in the hydrothermal fluid than there is CO2 in seawater. So there has to be an additional source. It also tells us that the formation of methane has to be independent of fluid circulation, active fluid circulation. Now, this is just the relative abundances of methane, ethane, and propane in different hydrothermal systems. They all show very similar patterns, suggesting that there is a common source in formation conditions. And there's David Wang and Shoei Ono's group who did the clumped isotopal loads of the methane and found that they basically all show the same, yield the same temperature of about 300 degrees C, same delta D and delta 13 C values, independent of the vent fluid temperature. So that says that the vent fluid temperature really doesn't have an effect on the formation of methane. There were early studies that suggested this is all magmatic methane, but there are problems with the solidus or liquidus or solidus of these. This hypothesis would be unreasonably low. We were at the Mid-Cayman Rise in 2012 and brought rocks home that were loaded with these fluid inclusions that I showed on my first slide. And these fluid inclusions form these trails. And the way this works is that you have a fluid that is percolating through a fracture, and the fluid is in chemical equilibrium with the rock, and the rock is able to heal and trap these fluids as fluid inclusions. We did a global survey of 160 samples or so, where we measured the composition of fluid inclusions using Raman spectroscopy, and by far most of them contained abundant methane. In fact, all of the gabbro, which is lower oceanic crust, and like 2/3 or 3/4 of the mantle rocks. This is what they look like. All in different environments, they all look the same. When you do, sorry, I'm rushing through this in the interest of time. These are backscattered electron images and element maps. So we can see, for example, the formation of sylvite here, which is a potassium chloride mineral. So these are the reaction products through serpentinization within these olivine-hosted fluid inclusions. So serpentine, brucite, I've heard this before, but magnetite as well as awaroite and pentamite. So these are examples of the Raman spectroscopy analysis that we made. So as the inclusions either contain hydrogen, a mix of hydrogen and methane, or methane only. And these are all Raman maps from different settings, and they all look the same, suggesting it's a global process that is occurring. So we extracted the methane from the rock and bulk analysis using a modified vacuum crushing device, and then analyzed the stable carbon isotopes of methane and ethane, and they broadly are consistent with the ones from vent fluids and gas seeps in ophiolite. Also did noble gases. I'm going to skip that. We had this came up with this model where we basically take olivine and water and bring it together at 600 degrees C and then just simply cool it. And now here, this dark gray area is where olivine is stable in the presence of water. When you decrease the temperature, the reactions start to happen, and olivine becomes completely unstable at a temperature of about 320 to 340 degrees C. And the temperature from clump isotope thermometry of David Blank's study was 310 plus minus 50 degrees roughly. So very consistent with this change in like the destabilization of olivine, which is really where we form most of the methane and hydrogen and consume most of the CO2. So CO2 is a little minus 20, log minus 20. So this is the last slide. The idea would be that we have an olivine-bearing rock that is cooling from magmatic temperatures higher than 800 degrees C below the brittle ductile transition temperature. So that is above that temperature, the olivine behaves plastic, so to say, ductile. Below that is brittle, so it can fracture, fluids can rush through. The olivine is stable at temperatures higher than 400 degrees C, so we have just water trapped in the olivine. When the temperature decreases further, below 400 degrees C, you start the formation or the serpentinization process to form hydrogen. And that hydrogen is at the same time as you produce the hydrogen and you consume the water, the water activity decreases, and this really favors the formation of methane. And eventually, the olivine host can dissolve or fracture, and then the fluid inclusion contents can vent to the seafloor mixed with seawater or hydrothermal fluid, and vent plumes or gas seeps on continental settings. And this model really explains a whole lot of observations that weren't compatible with this original model that just have CO2 and seawater, hydrogen for serpentinization, and make a bunch of methane. Yeah, I'll leave that last slide up, but won't repeat it. Thank you for your attention, and sorry I was running a little late. Questions?
So the CO2, the difference, you say the CO2 is not coming out of the seawater, it's magmatic CO2?
Yes, it's magmatic CO2 most likely. What I didn't dwell on is like the composition of the fluid inclusions. There's also graphite. There can be graphite in there, as well as carbonates. So you can imagine if you start out with magmatic CO2 and then you form graphite and a range of carbonate minerals, that leads to fractionation, which is why the carbon isotopic composition of the methane is not exactly that of the mantle value.
Anything else? Oh, it's time for speaker again.
Thanks. All right.
So Peter, what is the serpentinization in these layered intrusions? Somebody looked at it, like the roof and all those things?
Yeah.
The iron content is higher?
Yep, the iron content is higher, and the magnetite formation is
Much better.
it can be high, but not. There's Ben Tudelo.
Yeah.
He did that. Yeah, the Toulouse